Hello everyone, today I'm here to give you a quick overview of the control block program model inside the PDI Builder. To ease the explanation, I will use the Embention eVTOL configuration template, which is available on the Embention cloud. So it will be easy also for you to use it as a reference. Usually in Embention, we create our control logic using a PID loop. Usually we involve three different loops, the inner one which control the acceleration, the middle one which control the velocity, and the outer one which control the position. Since it's a VTOL, the control logic in this case will be a bit much complicated because we will need to create a fuse between control logic which is working for the multicopter mode and another one which is working for the fixed wing mode. In this case, we will compute some parameters which just decide when the platform can be considered to work in a multicopter mode or to work in a fixed wing mode. So I don't want to explain how we select this, but just to let you know that this value that we will see later on in the control logic have been computed in the control mix submodels. We can give a look, for example, at pitching, the first one. By using the phase switches, we can create different control logic for different phases of the mission. So, for example, in standby arm, flight control check, or initial, in which the platform is supposed to be on the ground, we don't need to control, so we can just leave empty this part. Instead, for what concerns the real flying phases, for example, we will use in these block programs, we will have the outer loop and the middle loop. So, for example, just considering the multicopter mode, so the first one, just ignoring the fixed wing part in this case, we will have a PID which, in order to understand how much we need to pitch, we will consider the desired front ground velocity and our current front ground velocity, which will compute the desired pitch. Then we have now some rate limiter, which are which aim is to reduce the variation or to limit the variation of the desired pitch in order to ensure the safety of the platform. And then with the desired pitch that we compute through the our current front ground velocity and the difference with the desired front ground velocity, we compute the side pitch rate through another PID, which is the middle loop. As I explained you before, through the values of the control mix 1 or 2 that which are computed inside the control mix submodels, we decide if we can use the multicopter PID or the fixed wing mode. And we are enabling or disabling this PID through the use of this bit. I want just to point out that the use of the PID loop is just one choice. There are other block that we can use that you can easily consult going in the add block menu and just checking on the control model. You can see that there is driver control filter, ACU control, fuzzy logic, PID, the one which are involved now, predictive control block, quaternion control, T-scale PID, and so on. And more or less, the what we saw here for pitching will be valid also for rolling and for yawing. So Now I want just to show you the to close the attitude control, the last loop, the inner loop. In the linear loop, we will just convert the desired roll rate, pitch rate, and yaw rate computed through the previous loop, um, um, passing through this block, which is a custom block. We will pass to the desired angular velocity, and then we will, through other PID, will compute the control output of the logic to ensure that the actual attitude is matching with the desired one. Similar case will happen for the thrust, which will control the thrust vertical, just simply checking the difference between the downground velocity and the desired downground velocity. And for example, is common use to put as a feed forward a thrust value which compensate for the weight. And for what concerns the throttle horizontal, since I want just to be reminded that this is a multicopter plus a fixed wing, because it's a eVTOL, so it can convert. So we need to divide the logic for the throttle, for the vertical and the horizontal component. Lastly, when we compute all the control output, both for the throttle and for the attitude control, we are going to the last program, which is the control to servos, in which all the control output are fed in this actuator block. And in this actuator block, we can configure the settings of the servos, and we can select also the mixer matrix, so associating a control output to a movement of a servo. In fact, by simply accessing in the actuator block, we can just access the configuration of the motor and of the servos. In this case, we will have 4 different motors for the multicopter mode. So the eVTOL will work as a quadcopter in that mode. And then we have a pusher motor and the 2 elements, one on the right, one on the left. We can easily access here to the deflection limit. For example, we can look at the one of the right element, which will go from the minus 30 degrees to 30 degrees, and we can associate a control output to each of these deflections. So we will have a minus 30 degrees of deflection when the pulse will be at 0, and of 30 degrees when the pulse will be at the maximum. Now we can check also the mixer matrix just by clicking on edit. Through the mixer matrix, we can link the output of the control logic to the action of the servos. In this case, for example, we can just look at the thrust vertical for the multicopter mode. So if we want to increase the altitude of our platform, we will just increase the action of each motor, increasing the outcome of the thrust, and so gaining height. It will be the same, for example, for the roll in multicopter mode, in which if we want to roll positive, so roll towards the right, we will decrease the action of the motor on the right, the first one and the second one, and we will increase the action of the motor on the left. And the same will work for the pitch on the multicopter mode, the yaw on the multicopter mode, but also for the thrust and pitch, roll, and yaw control for the fixed wing mode. And obviously also this control matrix can be customized as you wish. The number of actuators can be increased, and also the number of the control output. Lastly, we can look at the output of the actuator block, which will be the PWM that we will be used to control the actuators, or some variables also that will be used to that can be sent by CAN or through a serial connection to serial port to the actuators, and also some bits that are reporting if that servos are saturated or not. This was just a simple overview for the control logic and how they're implemented in the block programs in Veronte. For any further information, please don't hesitate to contact us. Thank you for your attention and see you in the next videos.